All this week we're going to discuss gravitational waves. So today I'm going to go somewhat quickly through some material which I'm hoping is mostly review from the previous class. In particular, we're going to talk about gravitational waves propagating in the weak field regime, how to derive the quadrupole formula for non-relativistic sources of gravitational waves, and expressions for the energy and angular momentum in gravitational waves. And then starting on Tuesday, Huan Yang will be lecturing, and he'll tell you all about perturbed black holes and how they can source gravitational waves, and a little bit about how gravitational waves are detected. So we're going to be working today in the weak field regime. And that means that we're going to use the approximation that our metric tensor is close to the flat space metric plus some small correction, which we'll call h. And to begin with, we'll just be working to linear order in h. So for example, if we want to raise our metric, we just pick up a minus sign. And then the other order terms are just non-linear in h. So we're going to be working in harmonic gauge, which is already familiar to us from the discussion last week. So that just means that box of the coordinates is equal to 0. And since we already wrote down the equations for the generalized harmonic formulation of Einstein equations, we can basically just set all the source terms to 0, and then we can even drop all the nonlinear terms in h, and then we get this. And of course, this is just now it's the flat space, covariant Laplace operator. Yeah, and so you'll recall that to derive this equation, we're using the trace reverse form of the Einstein equations. So we can also trace reverse this back, in which case we get the following. And so we'll find it convenient to work with this quantity here, which we'll call h bar, which is the trace reversed metric perturbation. And it has the opposite trace as h. Though when we work in vacuum, so we can actually ignore this term, we'll actually choose a gauge where h is traceless, and then there won't be any difference between h and h bar. So if we work out what this harmonic gauge condition means in terms of this h bar, it's actually equivalent to the following. You can work out that on your own. But if you look at this here, this is called a Lorentz gauge, an analogy with the gauge in electromagnetism, where you choose the divergence of the 4-vector potential to be 0. But just like in electromagnetism, we still have some coordinate degrees of freedom that we can play with. So, for example, in electromagnetism, if we have our 4-vector that satisfies this Lorentz gauge, we can still add the derivative of some scalar. And if the scalar satisfies this condition, then it'll leave our Lorentz gauge condition still satisfied. So we can add an arbitrary potential that satisfies this equation. And similarly for the Einstein equations, we can still perform a coordinate transformation as long as this extra bit of the coordinate transformation, again, doesn't upset our harmonic condition. And of course, we don't want this extra coordinate transformation to be large so that it'll take us away from our flat space metric. So just an infinitesimal coordinate transformation. So we'll use those extra degrees of freedom in a second. So now I want to talk about the propagation of gravitational waves. So in particular, we're going to restrict to the wave zone where we can assume that the non-propagating metric degrees of freedom are 0. So for example, there's going to be a Newtonian potential part to the metric. Near the sources, we can't ignore that. But that won't propagate, and far away, we'll just have the sort of radiating degrees of freedom. And we'll also, assume vacuum. So in the wave zone, we're going to use these 4 extra gauge degrees of freedom by choosing these 4 components at C. To impose the following conditions. So this will be moving to what's called a transverse traceless gauge, which I'll denote with a TT. So first I can choose the components of H that have one time component and one spatial component to be 0. So it uses 3 degrees of freedom. And then I'll also impose that H be traceless. So in this case, our TT H is just equal to this trace reverse one as well. So it actually turns out, so we used up all our 4 coordinate degrees of freedom in the wave zone, but it turns out we actually get one other condition for free. So to see that, if we write down our Lorentz condition, so by this condition here, these are all 0, so we can just ignore this. And then we can just choose HTT to be, or sorry, H00 to be 0 initially at t equals 0, and then it'll remain 0 for all time. And we can do that just because if we look at this equation here applied to H00, we just get that this is true when we have no sources. So we can impose this when we have no sources. Okay, and so now we're just left with this basically wave type equation for each component of our TT metric perturbation. And this will actually have plane wave solutions, which we can write in the following form. So this is just some constant matrix here. And you'll notice now I just am just using the spatial indices because, as we just argued here, all of the time components are 0. So we can just plug this into our equation of motion there. So we just, each of these derivatives will just pull down one of these factors of Ka. And then we basically get that Ka contracted with itself times our metric perturbation is 0. So if we want to have a non-trivial metric perturbation, we need Ka to be null. Okay, so let's choose some specific coordinates. We can basically choose Ka, the spatial component, to point in the z direction, which means that Ka has to take the following form. So we want just a non-zero component in the z spatial direction, and then from the requirement that's null, we can deduce the time component. It has to be the same. Okay, so that's just using this equation. We can also use our Lorentz gauge condition on this plane wave solution. We just pull down one factor of k. And this basically gives us, then we contract k with our metric perturbation, we have to get 0, which means that metric perturbation has to be transverse to the direction of propagation. So that means we can rewrite this constant tensor coefficient the following way. So we can do this because first all the z components have to be 0 by this transverse property. So those are 0. This metric has to be symmetric by definition. And then we also know that it has to be traceless by construction. So the trace has to be 0. So that's why we get the minus sign here. And so here, of course, the h plus and h cross coefficients correspond to the two polarizations of the gravitational wave. So to see this, we can note that in this TT gauge, geodesics are, if just sitting at some constant coordinate position, actually corresponds to a geodesic. So we can write two geodesics in this TT gauge as the following. So have one just moving at some moving forward in time, and then sitting at the origin, and then another geodesic also moving forward in time and sitting displaced in the x direction by some distance L. So if we just have a wave with the H plus polarization, and then we look at the proper distance between A and B. So just using the fact that our metric is flat space plus this correction, we get the following for the square of the proper distance. Or using the fact that H plus is small, just take the square root. So this means that as this gravitational wave propagates through, the distance between these 2 points that are displaced in the x direction oscillates like this cosine. So if we look at a set of test particles that are initially arranged in a circle, and then look at what the H plus polarization of the gravitational wave does, it'll distort it in one direction, and then the other direction, oscillating back and forth. And then the H cross is the same thing but rotated. So we'll start with the circle of test particles that are freely falling. and they'll oscillate like that. We can also note that if we rotate our coordinates by some angle phi about the z-axis, then our two polarizations rotate in the following way. So this is the reason that people refer to gravitational waves as being spin 2, because of how they change about rotations under the z-axis, or about the axis that's the direction of propagation. So this factor of 2 is why the graviton, if we can construct a quantum theory of gravity, would be a spin 2 particle. So any questions about that? Hopefully that's mostly review. Okay, so next we're going to talk about how these gravitational waves are actually generated. Okay, so now we don't want to restrict ourselves to vacuum. We'll have sources that actually generate these gravitational waves, and we can't necessarily impose this TT gauge in the source zone, because we'll have these other metric degrees of freedom that don't radiate. However, we still do have this equation over there in terms of the trace reverse metric perturbation. Write it again. So this is just, again, a wave equation for each of these components of the trace reverse metric perturbation. So we know one way to solve the wave equation using the approach of a green function. So the idea of a green function is, instead of solving, choosing some source and then trying to solve it, let's solve it once and for all in such a way that we can reconstruct it for an arbitrary source. So the green function satisfies, again, the wave equation, but with a delta function source. And here, this derivative operator is just with respect to this coordinate, not the barred coordinate. So you can look in your electromagnetism textbooks, for example, for the solution of this. It's given just by the following. And so this is the delta function, and this is the related theta function, which has the following property. That it's 1 when this argument is positive. And then it's 0 otherwise. So there are actually 2 Green's function solutions, and we chose one of them. Does anyone know what this solution is called?
Retarded one?
Yeah, so this is the retarded solution. So once we have this green function in hand, we can solve for the metric perturbation for an arbitrary source using the following relation. Here, this integral is over the barred coordinates.
If we were to have a boundary, we have another term, right? In this expression, when you have a boundary, right?
Yeah, so I'm assuming that the sources are isolated. So if we go far enough away, then there's no matter,
Okay.
right? Like in the wave zone, for example.
Okay.
Yeah, exactly. Yep, so we can just plug in that definition here. We get the following. So this is the time coordinate that TAB is evaluated at, and this is the spatial coordinate. So just using that delta function to get rid of the time variable. And this quantity here is called the retarded time. So if we look at this integral, to find our metric perturbation at some given point xi and at some time t, we basically need to look at its past light cone. So look back to some retarded time tr and find this value and evaluate this stress energy tensor at xi bar. Okay, so these integrals will be easier to do in Fourier space. So that's just the definition of Fourier transform. And if we plug in this relation right here, So I plugged in the definition, and I also use this relation between t and the retarded time t. And so then we can use this time integral with respect to the retarded time to Fourier transform the stress energy tensor. And then we're left with the following. Okay. And if we also Fourier transform our Lorentz condition, we can note that it just becomes this. So that's just Lorentz condition in Fourier space. So we don't have to worry about computing the time components of h tilde. We just compute the spatial components, and then we can recover the rest from this relation. Okay, any questions about that so far? So to make some more progress, we need some additional assumptions. So basically what we're going to assume is that we have our source zone where maybe we have some stress energy that's not zero, some extent. And then we're going to assume that we're some observer very far away at some distance r. And we want to assume basically that if we look at the gravitational waves coming from this source zone, so first of all, we want to assume that the distance is very large compared to this gravitational wavelength, or 1 over the frequency. And then we also want to assume that the extent of our source is small compared to the wavelength of the gravitational radiation. So this second assumption, will be true if, for example, we have some compact sources and they're moving slowly compared to the speed of light. So with these assumptions, we can make the following approximation. So this term that sits inside the integral can basically assume that the distance between our observer and some part of the source is just approximately given by r. Let's call that, for example, the distance to the center of mass or something like that. And then we can also approximate this as r as well. And that means we can pull it out of this integral over the volume. And so we just have to calculate this remaining part that's this spatial volume integral of the Fourier transform of the stress energy tensor. So in order to calculate this, we're going to use a couple of tricks. One is reverse integration by parts. And the other is just the fact that the stress energy tensor is conserved. So we wrote this using reverse integration by parts. If we work out that, we just get back to here. But so this term is a total integral. So we can set it to 0, again, assuming that the far away, there are no sources. And then this term, just using the conservation of stress energy, we can rewrite it as the following. So then we can rewrite this Okay, so here, just pull out this factor of I times omega, and then I use the fact that the stress energy tensor is symmetric to basically symmetrize this term here with this factor of 2. Okay, so just use the same tricks again. Reverse integration by parts. And so again, we can get rid of this total derivative and use conservation of stress energy to rewrite this term as the following. Get another factor of I omega, basically. So this term is just the quadrupole moment, or rather the Fourier transform of it. So we call that I, capital I. right, so just to summarize, if we plug in this part of the integral we just calculated here to the formula at the top, get the following in Fourier space. Or if we go back to real space, where these dots represent the time derivatives. And we should remember that we're evaluating this at the retarded time. So just quickly, we should ask ourselves the question, why the leading order contribution to the gravitational waves actually comes from the quadrupole part. So there are lower order contributions, of course. The first would just be the monopole, which would just be integral over the energy density. Of course, that's basically just the mass in our source region. So that's not going to give us gravitational waves. And in fact, just in spherical symmetry, Birkhoff's theorem tells us that if we're in a vacuum, then we have a stationary spacetime. There are no gravitational waves. So the next higher order would be the dipole. So I would just be integrating our energy density with 1 power of the coordinates. And so does anyone know why we don't have dipole radiation? So for example, in electromagnetism, you do have dipole radiation, but not in gravity.
I think it's related to the gauge freedom we have here, that the transformation, coordinate transformation we can do somehow.
Yeah, so in some sense, we can always go to the center of mass frame where we won't have this displacement. Another way to see it is that basically in electromagnetism we have positive and negative charges, but here there's only positive mass. Yeah, and so just as a quick note, this quadrupole formula doesn't always hold in the weak field regime. We made some additional assumptions. So for example, in the first week we talked about these like boson clouds that could form around black holes through super-8 instability. So you have some black hole, you have some cloud around it. And we said that this cloud can be sort of the characteristic length scale is set by this effective Bohr radius, which is just given by the mass of the boson times this alpha parameter, the inverse of that. And this alpha parameter is just the mass of the black hole times the mass of the particle. And in the non-relativistic regime, this is actually much less than 1. But on the other hand, this cloud is oscillating at some frequency omega, which is just close to the mass of the particle. And so the gravitational waves are just going to be at twice that frequency. So you can see that in that case, we don't actually have that, the extent of our source is much larger than 1 over the frequency, or basically the wavelength of the gravitational waves. So in this case, basically, the different elements of the cloud are, you can think of them as exciting gravitational waves that add up incoherently, because they might be out of phase or something like that, so you can't actually apply the quadrupole formula. We can still use, we're still, if we're in this limit, we're still in the weak field regime, so we can use the Green's function method, but we can't use the quadrupole formula. This is in contrast with the circular binary case, for example. So there, if we have two objects of mass m and they're in some circular orbit or something like that, and call this distance between them 2r. There the frequency of the gravitational waves is going to be twice the orbital frequency. So if we just plug in the relation for a circular orbit, we just get this. So since if we're in the non-relativistic regime, m over r will be small, we do have this difference between the, where basically the distance between the objects is small compared to the wavelength of the gravitational waves. So the quadrupole formula is fine there. So the last part of class, I want to talk about the energy and angular momentum in gravitational waves. So in order to calculate the energy and angular momentum in gravitational waves, we're going to write down sort of the effective stress energy tensor associated with gravitational waves. And there isn't actually a good definition of gravitational wave energy density localized to some point. So this will be gauge dependent. But it will allow us to calculate sort of fluxes of energy and angular momentum at infinity, which we can make meaningful sense of. Okay, so the idea is going to be to expand the Einstein field equations now to second order in the metric perturbations. This kind of makes sense because we would think that the sort of energy in the gravitational waves would be proportional to the amplitude squared, like other wave energy densities. So we need sort of second order equations. So expand our metric around some background metric again. Then we have the linear order perturbation. Then we need to satisfy the linearized Einstein equations. And then we'll have some second order metric perturbation. We can similarly expand our Ricci tensor. The Ricci to the background metric will just be 0 by construction. And then we'll have a first order and second order contribution. So the idea is, to first order, we just chose this H1 such that it satisfies the Einstein equations to, when we expand out the Einstein tensor to first order, plug in this metric perturbation, we get 0. But now if we go to second order, we have 2 contributions. So one will just be plugging in our next order contribution to the metric into our expression for the Einstein tensor, which is just linear in the metric perturbation. And then the other term that we have to consider is we look at the quadratic terms in the Einstein tensor and just plug in the first order metric perturbation. So these have to cancel out to satisfy the Einstein equations at second order. So linear and quadratic pieces. So the idea is just, let's just move this guy over to the right-hand side. And treat it like it's stress energy. So now I'm introducing this stress energy of the gravitational waves with a lower t. So it's just going to be quadratic in this linear order metric perturbation. And yeah, and so I want to be careful because this is not gauge invariant. But we can get around this by basically averaging over several wavelengths or periods of the gravitational wave. We can't localize the gravitational wave to some distance that's comparable or smaller than its wavelength, because we can always perform some metric transformation or something like that to make things look locally flat there. But if we extend over several wavelengths, we can. So, interested in time, I'm not going to go through actually working out what this is, but we can just write down what the answer is in TT gauge. So here these brackets represent averaging over several wavelengths, and that allows us, so to derive this equation, we just expand the Einstein tensor to second order metric perturbations, and then we also use this averaging to simplify things. So for example, when we have the average of some derivative of a term, we can just set that to 0. And when we have some term times a derivative, we can basically just flip the derivative and get a negative sign using this property again. So using those tricks, we can arrive at this equation. And then we can use that to now define an energy in gravitational waves. So at some time, we just integrate over some slice of constant time our sort of effective energy density. For example, if we plug in the plane wave solutions that we wrote down earlier, into this equation here, get something very simple. So this seems very sensible for waves. The energy is quadratic in the amplitude, and it's proportional to the square of the frequency. So we can also define a flux of energy in gravitational waves at infinity using this effective energy tensor. So here, this Ni is, so we're integrating some surface S at infinity with some unit normal Ni.
I have a question for that. Because for doing that, we've contracted this energy momentum tensor with t, like direction, right? To get the zero on to define a flux.
Yeah.
Can we still consider that a conserved flux, even though that vector wouldn't be a Killing vector because you have a gravitational wave passing, or?
Yeah. So I mean, the idea is that we're going very far away from our source.
So the gravitational wave is going to be weak, or?
Yeah. So that will be very close to flat space.
Okay.
But yeah, basically, to make this sort of rigorously well defined, you can, for example, if you start, at before some time, you have sort of a stationary spacetime, then you have some gravitational waves that pass through between time 1 and time 2, and then after that you have again a stationary spacetime. Then you can show that you can get a rigorous definition of the energy in gravitational waves that passes through to basically propagates to null infinity in between those two times. But otherwise it's a little bit tricky to define. And again, that's assuming asymptotically flat and so forth. Yeah, and so similarly, we can define a flux of angular momentum. This is just basically taking the flux of momentum and taking the cross product with R. And so you can derive approximations for these expressions assuming the quadrupole formula. So it's a little bit of a long calculation since we're out of time. We'll go through it. But the basic idea is you convert this h bar ij into a TT gauge. You use these expressions relating h bar to the quadrupole moment, and then you convert back. You plug this into this expression for TAV, and then you convert back to the regular metric perturbation in the non-TT form. So let me just write down those answers. So for flux of energy in gravitational waves, we get the following, which is a pretty simple form. So 3 time derivatives. And we're evaluating at the retarded time. And this I with the slash is the reduced or trace-free part of the stress energy tensor. And similar, we can get an expression for the angular momentum carried in gravitational waves. So this actually comes from, as you can see for that expression, basically the non-radial components of T0a. So, for example, if we have a binary that's with some circular orbit, it's going to emit waves. And if we look at the gravitational waves in the equatorial plane, these wave fronts won't be entirely circular because it's sort of be led by where the position of the binary is. Hence, there will be a non-zero component to that. It'll just go like radius to the third power, and when we multiply by this other factor of r, we can get a finite expression when we take this integral to infinity. So even more tedious calculation, you get the following. And you can see sort of more details on this derivation, for example, in MTW. I think it's chapter 36. So let me end here and take any questions.